For question 11, we're being asked to consider the function f of x is equal to e to the cos 2x, where x is between pi over 4 and 5 pi over 4. And we're being asked to find the coordinates of the points of the curve y equals fx, where the gradient is 0. So how do we find the gradient? Well, the gradient is the derivation, so we need to derive that function. But what is that actually doing? If we consider a curve y equals x squared, and we consider a point on this curve, the slope of the curve at that point is going to be a tangent to that dot. And you can see here that it's going to be certainly a minus number. As we move the dot along, the tangent changes as the curve is curved. And as you can see that as we increase in x, our slope is increasing. It's still a negative number at the start, as your curve is still pointing downwards. However, it's starting to slowly level off until it reaches the origin, where you can see that the curve does equal to 0, and then it keeps going along and keeps increasing. So you can see here that the red line, the derivation of f of x, is equal to 2x, and this is the slope. This is a function. This is a function that allows us to put in an input x and find out the slope of f of x at this point. Now, for simple functions like x squared, the derivation can be quite straightforward. However, for more complicated functions, we have different tools at our disposal in order to get the derivation of that function. One of these tools is the chain rule. So let's take an example. Let's take a function h of x, which is equal to sine of x squared. Now, in order to use the chain rule, we need to split this up into different components. We need to start by taking the innermost function. So in this case, the x squared. We let that equal to g of x, and we do the derivation of this. So the derivative of g of x is 2x. Next, we move out to the other function, which in this case was the sine function. And what we're going to do is we're going to say f of u is equal to the sine of u. And we're going to do the derivation of this function, where the derivation of f of u is equal to cosine u. The chain rule says that the derivative of h of x is equal to the derivative of f with the input g of x times by the derivative of g of x. So in this case then, we have the derivative of h of x is equal to the cosine of x squared times by 2x. This method is given in your formula booklet, and you should be able to use it quite easily. So going back to the question, we're asked to find the coordinates of the point of the curve where the gradient is 0. So taking our function f of x is equal to e to the cos 2x, and applying the chain rule, where we'll set g of u equal to the e to the u and h of x equal to cosine of 2x. Taking the derivative of both of those, we have the derivative of g of u is equal to e to the u, and the derivative of h of x is equal to minus 2 sine 2x. Next, applying our chain rule formula, where the derivative of f of x is equal to the derivative of g of h of x times by the derivative of h of x. And substituting in the values we have that the derivative of f of x is equal to e to the cosine 2x times by minus 2 sine 2x. And we set this equal to 0 so that we have the coordinates of when the derivative is 0. Now, there is no value of x that can set e to the cosine 2x to 0. However, there is a value of x that can set sine of 2x to 0. So that's what we go with. We go with the sine of 2x is equal to 0. Now we know that the sine of an angle is equal to 0 at multiples of pi. Therefore, dividing that across by 2, then we have x is equal to 0, pi over 2, pi, and etc. And then it's very important to note that we're asked for the coordinates. So we're asked for the coordinates where we give an x and a y component. So we have when x is equal to 0, y is equal to what? When x is equal to pi over 2, y is equal to what? And substituting that in, we then get these coordinates. Looking at part B, it asks us to use the second derivative of each point found in part A to show that the curve y equals f of x has 2 local maximum points and 1 local minimum point. What is a second order derivative? Well, just like a first order derivative, it tells us the rate of change of something. except in this case, instead of telling us the rate of change of the function, it tells us the rate of change of the first derivative. So what does that look like? Well, if we plot the function f of x is equal to x cubed, we can also plot the first order derivative of that function, which is 3x squared. So this tells us what is the slope of the original function at all the different points. And then we can also plot the second order derivative, which tells us the slope of the first order derivative, again at each of the points. And you can see how this changes for different values of x. The second order derivative tells us how quickly the slope of the original function changes, and we can use that to analyze concavity. To solve part B, we need to take the derivative of what we solved in part A. The first order derivative is equal to e to the cosine 2x times by minus 2 sine 2x. In order to take the derivative of this, we need to use the product rule. The product rule works by splitting the function into its two individual functions, label them u and v. We have then u times the derivative of v plus v times the derivative of u, and this is our second order derivative. In this case, if we label e to the cosine 2x as u, we would have e to the cosine 2x times the derivative of minus 2 sine 2x, which is minus 4 cosine 2x, plus v, which is minus 2 sine 2x, times by the derivative of e to the cosine 2x, which is what we calculated in part A. So it's simply again e to the cosine 2x times by minus 2 sine 2x. We're asked to solve this at the coordinates that we discovered in part A, namely when x is equal to 0, x is equal to pi, and when x is equal to pi over 2. Now at these points, the cosine of 2x goes to 1, 1, and minus 1 respectively, and the sine of 2x goes to 0 for each of these, so we can simply ignore the second half of what we have solved earlier for the second order derivative. Then at these points, at x is equal to 0, the second order derivative is simply just minus 4e. This is less than 0, so that's a maximum. At x is equal to pi, again we have the second order derivative is equal to minus 4e, so again less than 0 and a maximum. And finally at x is equal to pi over 2, the second order derivative is equal to positive 4 divided by e. This is therefore greater than 0, so it's a minimum. For part C, we need to sketch the graph using the information we've solved from part A and from part B. Now we know from part A that the graph is going to have a 0 gradient at the coordinates that we solved, so 0e, pi over 2, 1 over e, and pi e. Additionally, from part B, we know that when x is equal to 0 or pi, these are going to be maximum points. And when x is equal to pi over 2, this is going to be a minimum point. And so we simply need to draw the curve hitting those points and then simply just label those points with the values that we know. This is all you need to do for this question. Please make sure to either label the points or put the values clearly on the axes, so it is obvious that you've added this information to the graph. Question D is asking us to use the Maclaurin series, starting with cosine 2x and basically expanding up until we can capture our whole function, up to the terms x to the 4. The Maclaurin series is a method whereby using information from higher and higher order derivatives, you can slowly start to get a better and better approximation of the function you're looking at. How it does this is it's looking at the slope and how that slope changes and etc. around the 0 point. In the animation you can see what happens as you increase the series. However, I will say that there is a very good video here by the channel 3 Blue 1 Brown on Maclaurin and Taylor series, which I highly recommend. For the first part, to find the Maclaurin series of cosine of 2x, we are given in the formula bucket what the Maclaurin series is for the cosine of x. Obviously, we need to, in this case, replace the x with 2x. This gives us that the cosine of 2x is equal to 1 minus 2x all to be squared all over 2 factorial plus 2x all to the power of 4 over 4 factorial and continue. And simplifying a bit, that's cosine of 2x is equal to 1 minus 2x squared plus 2x to the 4 all over 3 and continue. For part 2, we're being asked to expand that to find the Maclaurin series for e to the cosine 2x minus 1. Again, in the formula booklet, we're given the Maclaurin series for e to the x. This is 1 plus x squared all over 2 factorial plus x cubed all over 3 factorial plus x to the 4 over 4 factorial. Solving for the factorials, we can replace 2 factorial with 2, 3 factorial with 6, 4 factorial with 24. As we know already what the Maclaurin series is for the cosine of 2x, we need to adapt this slightly as we're asked for the cosine of 2x minus 1. Obviously all we need to do here is subtract 1 from each side. So this gives that the cosine of 2x minus 1 is equal to minus 2x squared plus 2x to the 4 all over 3 and continue. And then we just need to substitute that in for x in our e to the x Maclaurin series. So e to the cosine 2x minus 1 is equal to 1 plus minus 2x squared plus 2x to the 4 all over 3 plus minus 2x squared plus 2x to the 4 all over 3 all to be squared divided by 2 factorial and continue. Multiplying this out and only keeping the terms that go up to x to the 4, we end up with 1 minus 2x squared plus 2x to the 4 all over 3 plus 2x to the 4. And finally, tidying up, we have 1 minus 2x squared plus 8x to the 4 all over 3. For part 3, to write down the Maclaurin series of our original function e to the cosine 2x, looking at this, we can see that that's equal to e to the power of 1 times by e to the power of cosine 2x minus 1. In this case, the 1's will cancel, as when the base is the same, you add the powers. All we need to do here is substitute in what we've already solved in part 2, and we end up with e times by 1 minus 2x squared plus 8x to the 4 all over 3, which, solving out a little bit, is equal to e minus 2e x squared plus 8ex to the 4 all over 3, and continue. For part E, we're being asked to use the first two non-zero terms in the Maclaurin series to show that if we integrate our original function between the limits 0 and 1/10, to show that this is approximately equal to 149e all over 1500. To do this is quite straightforward. We simply start replacing e to the cosine 2x with the first two terms of the Maclaurin series that we've already evaluated. So setting that approximately equal to the integral between 0 and 1/10 of e times 1 minus 2x squared, we can factorize out the e as the integral of e is just e. So we're left with e times the integral between 0 and 1/10 of 1 minus 2x squared. This is a fairly simple integration, and the result is x minus 2x to the cubed all over 3. All we have to do now is substitute in the values for our limits, where we get e times by 1 over 10 minus 2 over 3000. All we need to do then is to start simplifying. This is equal to 298e all over 3000, and dividing above and below by 2, we have 149e over 1500. Thank you so much for watching. I hope this tutorial made things clearer and helped you tackle this question. Don't forget to like, subscribe, and hit the bell to stay updated when more questions are answered. If you have any questions or need any more help, please drop a comment below and I will get back to you. Until next time, keep practicing and good luck.